Okay. Okay, so this evening we want to talk about something called conservation of linear momentum. And we want to talk about this conservation of linear momentum in terms of collisions when objects collide, and also in terms of explosions. So we want to talk about what we mean by conservation of linear momentum and where can we use this conservation of linear momentum. That's what we'll talk about. Okay, so we'll see what the principle of conservation of linear momentum says. What's the statement of the principle of conservation of linear momentum, and how can we use this conservation of linear momentum to work out problems. Then we'll also look at two types of collisions which can happen. One of them is elastic collisions. Now this is a collision in which the total kinetic energy before the collision and after the collision is the same. And there's another type of collision called inelastic collisions. Now this is usually the most common type of collision between bodies, in that there is a change in the amount of kinetic energy which is there available before the collision happens and after the collision happens. So we will talk about kinetic energy during this lecture, and the types of collisions. Then, of course, we'll see how this type of elastic collision and inelastic collision, how we can bring in kinetic energy, how we can explain things, and also how we can use the fact that the kinetic energy in an elastic collision is the same before the collision and also after the collision, the total kinetic energy. Okay. So the first thing we want to look at is something called the principle of conservation of linear momentum. And we are going to use this principle of conservation of linear momentum in the case where there is an explosion happening or when there is a collision happening. The other thing which I want to bring to your attention is that you can only use this conservation of linear momentum principle on the condition that there is no external force which acts on the objects you're looking at. So if there is no external force acting on any of the objects you are looking at, the objects which are about to collide or the objects which are exploding, it means that the velocity of these objects does not change, because it's only an external force which can cause the velocity of an object to change. Using Newton's second law of motion, if you've got an external force or a resultant force F is equal to ma. So if an external force F is present, then that external force is going to change the velocity of the object. It's cause an acceleration. So under what you're looking at here, there is no external force which acts on any of the objects in question. This means that the velocity of the objects you are looking at, the objects which are about to collide or after the collision has happened, the velocity is the same. So you're talking about objects which are moving with constant velocity. So some objects have to move with constant velocity. Of course, you can also have objects which are not moving, objects which are at rest. So if an object is at rest, we know that the velocity of such an object is going to be equal to 0. And if the velocity of an object is equal to 0, then we know that that particular object has got no linear momentum. The linear momentum is equal to 0. Okay, so that's the first thing I want to bring to your attention here. When you're looking at conservation of linear momentum, there should be no external force acting on any of the objects. If there is an external force, then that external force will cause the object to accelerate, meaning that the velocity of that particular object will increase. Okay, so if the velocity of an object is increasing, then you can't use this principle of conservation of linear momentum. So what does it say? Basically, it says, as the name says, conservation, it says that the total linear momentum is always conserved. Okay, and it's always conserved in the case when, and we're interested, the total linear momentum is always conserved everywhere. And in our case, we are going to investigate the case where an object collides or there's an explosion. So the principle states that the total linear momentum, which is plural for momentum, so the total linear momentum of bodies before they collide or explode is the sum of all the linear momenta accounting for their direction will be the same after the collision or after the explosion. So if you have, so what this is saying is that if you have a bunch of bodies moving or some of them are at rest, so if the object is moving, it has got velocity, so you multiply the mass of that particular object times the velocity. So for each of these objects, you work out the mass times the velocity. That's the linear momentum of this particular object. Then you add the linear momentums of these objects before they collide. So you add the linear momentum of these objects before they collide or before they explode. The total linear momentum you're going to get of these objects before they collide or after the explosion is going to be the same as the linear momentum after the explosion or after the collision. So basically, that's what conservation of linear momentum says. It basically says that the total linear momentum before collision or before an explosion is equal to the total linear momentum after collision or just after the explosion. Again, you should note that in this case, for this thing to work, there should be no external force which is acting on any of the objects which are under consideration. So how do we put this into practice? So we look at two cases. We look at a case where we've got two masses. These objects with mass m1 and m2, and they're going to collide. Okay, so you've got two objects with masses m1 and m2. Before they collide, these masses are moving with their velocities u1. U is the velocity of the we are using u to denote the velocity of an object before it collides, and we are using v to denote the velocity of an object after the collision. So in this case, the velocity of the first object, which has got mass m1, before it collides, we denote it as u1. The velocity of the second object before it collides with the first object, we are denoting that to be u2. This u1 and u2, these are velocities. Velocity is a vector, mass is a scalar. Okay? Then after they collide, they move away with velocities v1 and v2. So the velocity of these objects before collision and after collision are different or the same. We don't really care very much at this particular point. What we want to show is how to put into practice this this principle of conservation of linear momentum. Okay, so in this case, so if this is what you have, if you have mass m1 and m2 which have velocities u1 before, that's a velocity before collision, and u2, and you've got mass, and after the collision these objects have got velocities v1 and v2, then you can apply the conservation of linear momentum as follows. Total linear momentum before collision, just before collision, must be equal to total linear momentum after collision. So total linear momentum before collision must be equal to total linear momentum after collision. Okay, now direction is very, very important when you're talking about vectors, and linear momentum is a vector. So direction is very, very important. When you look at these velocities u1,
Excuse me, sir.
yes?
There's some people that would like to join.
Oh, okay. Yeah. So like I was saying, direction is very, very important in this case. When you look at this velocity, the velocity of the mass m1, which is u1, and the velocity u2, it's a vector. It has got size. It also has got direction. So usually we are interested in enforcing this conservation of linear momentum along the x direction. We are interested in enforcing this conservation of linear momentum along the y direction. If we make sure that the total linear momentum before collision along the x direction is equal to the total linear momentum after collision along the x direction, then also the total linear momentum before collision along the y direction is equal to the total linear momentum after collision along the y direction, then this can happen. Then this becomes true. So there's something more we need to do. For this to be true, this total linear momentum before collision equal to total linear momentum after collision, we need to make sure that this statement is true along the x direction. It is also true along the y direction. We need to make sure that this is the same. The linear momentum is conserved before collision along the x direction, and it's conserved after collision along the x direction. Linear momentum is conserved before collision along the y direction. Linear momentum is conserved after collision along the y direction. So for us to do that, we need to ask ourselves, how much is the velocity of the mass before collision, which is u1, the first mass before collision, which is u1, how much is this velocity along the x direction? And how much is this velocity along the y direction? That's where these components come in, u1x. So you need to find out what is the velocity of the first mass along the x direction before the collision happens. So that you have to find the component of this velocity along the x direction, u1x. You also need to ask yourself, what is the velocity of the first mass before collision along the y direction? So you need to find u1y. Then you come to this one here. You find out what is the velocity of the second mass before it collides along the x direction, that is u2x. What is the velocity of the second mass before collision along the y direction, which is u2y? So for these velocities before they collide, before the masses collide, you need to know what is the x component of u1 along the x direction, what is the y component of u1. You also need to know what is the x component of u2. You need to know what's the x component of y component of u2. Then after the collision, the masses are going to have different velocities, v1 and v2. So you need to know how much is v1 after collision along the x direction, that is v1x. How much is v1 along the y direction, which is v1y. You also need to know how much is v2 along the x direction, which is v2x. You need to know how much is v2 along the y direction, which is v2y. So what I'm trying to say is, this statement which we have here, the total linear momentum before collision and after collision being equal, yes, this is true, but we need to enforce this statement along the x direction and along the y direction. And that is what we are doing here. In the x direction, we need to multiply the mass, the first mass, m1, we multiply it by the x component of the velocity of u1 before collision, which is u1x. Then plus, we multiply the second mass, which is m2. We multiply the second mass with the x component of u2, which is u2x. How much the velocity u2 is along the x direction. This bit here is going to give us, this thing we have highlighted here, gives us the total linear momentum before collision along the x direction. This should be equal to the total linear momentum after collision along the x direction. And how do we get the total linear momentum after collision along the x direction? We multiply the mass of the object, the first mass, u1, multiplied by its velocity after collision along the x direction, which is v1x. Then plus the mass, the second mass, m2, multiplied by its velocity along the x direction, which is v2x. So we are extending this statement here, total linear momentum before collision. Now we are extending it to the x direction. We are enforcing it along the x direction, which is what we end up having here. m1 u1x plus m2 u2x equals to m1 v1x plus m2 u2x here. If this is true, so we try to make sure that this is true. It's always true before collision and after collision. Linear momentum is always conserved. We also enforce this same requirement along the y direction. So in that case, we need to know the velocities of these objects along the y direction before the collision happens and after the collision. So that's going to be the first mass, which is m1, multiplied by the velocity of this first mass before it collides, but along the y direction, which is going to be u1y, plus the second mass multiplied by its velocity along the y direction, which is u2y. This bit here is the total linear momentum before collision along the y direction. This must be equal to the total linear momentum after collision along the y direction, and that is given by m1 multiplied by the velocity of the first mass along the y direction, which is v1y, plus the second mass m2 multiplied by the velocity of the second mass after collision along the y direction, which is v2y. So when you enforce this conservation of linear momentum, to make sure that linear momentum is conserved along the y direction and it's also conserved along the x direction, then this becomes true. Total linear momentum before collision will become equal to the total linear momentum after collision. So you need to enforce these two equations here. These two equations are very, very important. Okay. Now, linear momentum, conservation of linear momentum always happens. Always. It doesn't matter what kind of objects are colliding. As long as there's a collision or there's an explosion, linear momentum is always going to be conserved. It will be constant. And in this case, we are talking about the total linear momentum before the collision and after the collision is always going to be the same. The total linear momentum before the collision will be equal to the total linear momentum after collision. Now, we have also seen that if you have, like in this case, since we have got linear momentum, any object which has got linear momentum also has got kinetic energy. Any object you have seen using this relationship we showed last time, Ke, kinetic energy, is equals to half mv squared, which is also equals to p squared divided by 2m, where the p is the linear momentum of this particular object. So what this shows is that you can express kinetic energy in terms of linear momentum, or basically in a nutshell, any object that has got linear momentum also has got kinetic energy. The question is whether the total, since each object has got kinetic energy, before the objects collided, they had kinetic energies. Each object had its value of its own kinetic energy. Each object had its own kinetic energy before they collided. If you add the sum of the kinetic energy, you get the total kinetic energy. Are the total kinetic energies going to be equal before collision and after the collision? It turns out that sometimes the total kinetic energy before collision is equal to the total kinetic energy after collision. Other times, the total kinetic energy before collision is not equal to the total kinetic energy after collision. Usually, the kinetic energy before collision is more than the kinetic energy after collision. So somehow, after things collide, there is a loss of kinetic energy which happens. In those cases where the kinetic energy before, the total kinetic energy before objects collide is the same as the total kinetic energy after the collision has happened, Such collisions are what are called elastic collisions or perfectly elastic collisions. So collisions in which when objects collide, the kinetic energy, the total kinetic energy before the collision happens and after the collision has happened is the same. So in this case, the kinetic energy is being conserved. Okay, it's the same before collision and after collision. Such collisions are called elastic collisions. However, this is not always the case. This is a very, very special case where you have kinetic energy before collision and after collision being the same. In most of the cases, if there is a collision, you hear some sound. You hear a bang. Or when you touch where the things collided, there might be heat there. So objects, after they collide, they might heat up. Or there might be some change in energy. If there is change in energy, maybe some object might gain height. One object gains height. If it gains height, it means that that particular object has gained gravitational potential energy, or it loses height, it has lost gravitational potential energy. So in such a case, when you hear a bang, or objects collide, then they get hot, or one object collides, then another object gains height, in such a case, there's going to be a loss of kinetic energy. So if there is a loss of kinetic energy, it means that the kinetic energy after the collision is going to be less than the kinetic energy before the collision. And this is the most common type of collision. And such kind of collisions are what are referred to as inelastic collisions. So in an inelastic collision, there is a loss of kinetic energy between the colliding objects. The amount of kinetic energy they had before they collided and the amount of kinetic energy when you work out the total kinetic energy before collision and the total kinetic energy after collision, you find that they are not the same. Usually the total kinetic energy after collision is less than the total kinetic energy before collision in inelastic collisions, because kinetic energy is lost in the form of heat, it's lost in the form of sound, or maybe in terms of gravitational potential energy. One object might gain height, might go up because it has collided. In the case where there is no loss in kinetic energy before or after, so we're talking about kinetic energy is being conserved. So in such a case, you could work out the total kinetic energy before the objects collided. So this is going to be half m1 multiplied by u1 squared plus half m2 multiplied by u2 squared. So this is going to be the total kinetic energy before collision. This total kinetic energy before collision for an elastic collision has to be equal to the total kinetic energy after collision. So this is going to be equal to half m1 v1 squared plus half m2 v2 squared. So this is what you end up with. Are we clear on what we mean by a collision which is elastic and a collision which is not elastic, inelastic?
Yes, sir.
Okay. Next, we look at example number 1. So in this example, we have a bullet. So a 8-gram bullet fired horizontally into a 9 kg cube of wood, which is at rest and sticks in it. The cube is forced to move and has a speed of 0.4 meters per second squared per second after impact. Find the initial velocity of the bullet. Okay, so what we have here, of course, again, is when you're dealing with collision problems, you are assuming that there is no force acting on any of these objects, because an external force is going to cause any of these objects to move faster, to increase in velocity. So you are assuming that there is no force which is going to cause acceleration here. So the assumption we are making here is that when the bullet is fired from the gun it has got the same velocity. So it comes out of the gun with the same velocity. And with this velocity, which we do not know, which is what you're looking for, it strikes a wooden cube, which is at rest. So this cube, we know the mass of the cube is 9 kg. And since this cube was at rest, the velocity of the cube was 0 meters per second. So before the bullet collided with or struck the wood was at rest and it had a velocity of 0 meters per second and it had a mass of 9 kgs. The bullet, on the other hand, had a mass of 8 grams and we don't know what the velocity was, but that's what you're looking for. After the collision, the bullets get stuck in the wood, so both the wood and the bullet move. They become one, and they move, after the collision, they move with a velocity of 0.4 meters per second. So using this information, we can enforce conservation of linear momentum. We can enforce conservation of linear momentum, and we can use this enforced conservation of linear momentum to find out what the velocity of the bullet was. So we start with the velocity of the bullet. So we denote the velocity of the bullet as mb, m being the mass, then b being the bullet. So mb equals to 8 grams. However, we do not do calculation in grams, so we change these 8 grams into kgs, so it becomes 0.008 kgs. This is the mass of the bullet. Then we know that when the bullet is fired from the gun, it has a certain velocity which we do not know at the moment, and that's what you're looking for. So we denote the velocity of the bullet to be ub. Ub is the velocity of the bullet before the collision happens. So anytime you're talking about a collision, the velocity before something collides, that's denoted as u. So since you're talking about the bullet, you just denote it as ub here. Then we also know the mass of the wood. So we denote that as mw, m for mass, w for the wood. So mw is 9 kgs. And since the wood was at rest before it was struck by the bullet, then we denote its velocity, which is uw, the velocity of the bullet before it was hit by the bullet, to be 0 meters per second. So with this information, the mass of the bullet being 0.008 kgs, the velocity of the bullet being ub, the mass of the wooden cube being 9 kgs, and the velocity of the wood being 0 meters per second squared. With this information, we can find out what the total linear momentum was before collision. So the total linear momentum before collision is going to be the mass of the bullet times the velocity of the bullet, ub, plus the mass of the wood times the velocity of the wood before the collision. So in this case, the mass of the bullet is 0.008 kgs multiplied by ub, plus the mass of the wood, which is 9 kgs, multiplied by the velocity of the bullet, which is 0 meters per second. This 0 times 9 is going to give you 0. So at the end of the day, we end up having the total linear momentum before collision just being equals to 0.008 kgs multiplied by ub. So this is our total linear momentum before the collision. Next, after the collision, we know that the bullet and the wood become one. So they have a combined mass of mb plus mw. Since they become one, they get combined. The bullet gets stuck in the wood. So the bullet and the wood have got a combined mass of mw. So the combined mass is going to be 0.008 kgs plus 9 kgs, which is going to give us 9.008 kgs. So this is a combined mass of the bullet and the wood. But we are also told that after impact, the wooden cube moves with a velocity of 0.4 meters per second. So with this combined mass, the combined mass and this velocity of 0.4 meters per second, which is the velocity after impact, we can multiply the combined mass by this to get the total linear momentum after impact. So the total linear momentum just after impact is going to be the combined mass of the wood and the bullet multiplied by the velocity with which the wood and the bullet moves just after impact. That's going to be 9.008 kgs times the velocity of 0.4 meters per second, and this gives us a total linear momentum of 3.6032 kgs meters per second. So we have the total linear momentum before collision, which is this much. we have the total linear momentum after collision, which is this much. So we have to, this linear momentum before collision and after collision, they have to be equal. So we equate them as per the requirement that linear momentum be conserved. Total linear momentum before impact has to be equal to total momentum after impact. So that's going to be give us 0.008 kgs multiplied by UB should be equals to 3.6032 kgs meters per second. So this is what's supposed to have like this. We are looking for the velocity of the bullet, which is this one, UB. So we divide both sides by 0.008 kgs. So when you do that, you end up having UB equals to 3.6032 kgs meters per second divided by 0.008 kgs, and this gives us a bullet velocity of 450 meters per second. So this is how we find the velocity of the bullet by applying conservation of linear momentum. So you treat what the bullet is doing, colliding into things. When people are shooting things, then the bullet hits the target. You treat that as a collision, and if it's a collision, then you can apply conservation of linear momentum in this fashion. Then you get the bullet velocity as that much. Are we clear? Any question? Is it clear? Okay, if I don't get a response, I'll push on to example, example number 2. A 16 gram mass is moving in the positive x direction at 0.3 meters per second, while a 4 gram mass is moving in the negative x direction at 0.5 meters per second. They collide head on and stick together. Find their velocity after collision. So here again, we have this mass, which is 16 grams. So we're going to treat this 16 grams as our first mass. And the velocity of this first mass is 0.3 meters per second along the positive x direction. Now, direction is very important here. Where the object is going is very important because velocity is a vector. And since velocity is a vector, you're multiplying mass times a vector. What you end up with is linear momentum, which is also a vector. So direction is very, very important when you are looking at linear momentum. So in this case, since the mass, 16 gram mass, is going along the positive direction, we take this velocity before impact to be a positive velocity. Then this other mass, the 4 gram mass, is moving in the negative x direction. So it's going in the opposite direction. So we take this velocity of 0.5 meters per second to be a negative velocity. So this mass, we denote it as our first mass, so M1. So here, M1 is equals to 16 grams, but again, we don't do calculations in grams, so you need to change your grams into kgs, so you end up having 0.016 kgs. Then the velocity is along the this first mass is moving along the positive x direction. So in that case, our velocity, which is of the first mass, u, and since it's first mass, u1 is going to be a positive velocity of plus 0.3 meters per second squared. The second mass is this one, 4 grams. So we denote that as m2. 4 grams, and 4 grams in kgs is 0.004 kgs. And this second mass is moving in the negative direction. So the velocity of the second mass before it collides, u2, is going to be negative since it's moving in the negative direction. So this is where you're seeing that direction is important because we're dealing with vectors. Your velocity is a vector, so minus 0.5 meters per second square meters per second. So with this information, we can find what the total linear momentum is before these objects collide. One is 16 grams moving in the positive direction at 0.3 meters per second squared. The other one is 4 grams moving at 0.5 in the negative x direction. So how much is the total linear momentum? So the total linear momentum is going to be the first mass is going to be equals to the first mass multiplied by its velocity u1 plus the second mass multiplied by its velocity u2. So in this case, the first mass is 0.016 kgs times u1, which is a positive velocity, plus 0.3 meters per second, plus the second mass, which is 0.004 kgs times the u2, which is the velocity in the negative direction minus 0.05 meters per second. So when you do this calculation, you end up with a total velocity which is equals to 0.0028 kgs meters per second. So this is your total linear momentum before they collide. So there is that before they collide. And we are told after the collision, they stick together. So the two masses, this 16 grams and this 4 grams, they stick together, they become one mass, and they move with one velocity. So the combined velocity, since m1 and m2 stick together, the combined velocity is going to be m1 plus m2. This is going to be the mass of the whole thing which are stuck together. Then they move with a velocity we are looking for, which is the velocity after collision. We denote that as v here. So the combined velocity of the masses times v. So the combined velocity is 0.016 kgs plus 0.04 kgs. This is going to give you 0.02 times v here, and you multiply by v there. So you end up having the total linear momentum after collision as 0.02 kgs multiplied by v. So this 0.02 kg times v, this is your total linear momentum after collision. This which you have here is the total linear momentum before collision. Conservation of linear momentum requires that the total linear momentum before collision should be equal to the total linear momentum after collision. The total linear momentum before collision is this one. The total linear momentum after collision is this one, so they have to be equal. So you equate them. So 0.0028 kgs meters per second equals to 0.02 kgs multiplied by v. So you're looking for v, so you divide by 0.02 on both sides, so you end up having v is equals to 0.0028 kgs meters per second divided by 0.02 kgs, and this gives you a velocity v of 0.14 meters per second. So the two masses which have stuck together immediately after collision, they move away with a velocity of 0.14 meters per second. Immediately after collision, the velocity of these two masses is 0.14 meters per second. In the positive direction, this is a positive direction. This is a positive velocity. So it means that after collision, this mass, which was moving at 0.3 meters per second, and this mass, which was moving at 0.5 meters in the opposite direction, they will move in the positive direction with a reduced speed of 0.14. They will move in the positive x direction with a reduced speed of 0.14 meters per second. Are we clear?
Yes, sir, we are clear.
Okay, so we come to an end here. I'm not sure exactly. I don't think tomorrow it's possible for us to meet, really, because I've got things which I'm doing. I'm picking up people at the bus stop. Yeah, so we'll meet on Wednesday. Okay. So I'll see you on Wednesday. Then after that, if there is need for a makeup class, we can always do a makeup class sometime, but we'll have to discuss. All right. So yeah, we've come to the stop, the end. Unless people got questions, here for questions. Like I was saying before, this is going to be the last week of me teaching you people. Next week, someone else is going to be taking over from me. The reason is because I have got 3 first-year lecture groups I teach, while everyone else has got 2 lecture groups. So I need to remain with 2. So the person who will be taking over is Professor Calawero. He'll be teaching you, taking your PHY 1010. Then I'll stick with just the PHY 1015. And he's going to start next week, same time.
Right, sir.
Yeah. The recorded video will be uploaded to YouTube as usual.